people have trickled back in from the breakout room, so I'm happy to introduce our next speaker. Seppo Niemi-Colvin is a fifth-year PhD student at Duke University studying low-dimensional topology under Adam Levine, particularly focusing on knots in three manifolds other than the three-sphere. Seppo grew up in Raleigh, North Carolina before attending Bryn Mawr College for undergrad, where he realized he is not a girl. After his first year of grad school, he realized that not only is he not a girl, but he's specifically a queer man. In addition to mathematics, Seppo also enjoys visual arts, and during the summer of 2020, took a class on landscape painting. Today, Seppo will tell us about square pegs and round holes.
Hello. Let's get started with the talk. As I said, the title is Square Pegs and Round Holes. So as mentioned in the bio, I do low dimensional topology. So what does that even mean? Well, to unpack that first, you know what a manifold is, which is a space that when you zoom in looks like r to the n for some dimension n. And low dimensional topology studies manifolds of dimension 4 or less and their submanifolds. As an example, I have a torus up here. And if we zoom in, say to this patch, this will look like R2. So this is a two-dimensional manifold. Yeah. Furthermore, I've drawn in here two curves, which if you zoom into them, they look like R1. These are one-dimensional submanifolds. They're manifolds inside our manifold. And this is a particular case where we can easily picture it. Another example to keep in mind, well, this is a knot, and it is particular sitting inside R3. So R3, when you zoom in, looks like R3. That is a three manifold, and here we have a one manifold inside it. Another example of a three manifold would be the three-sphere, which you can think of as the points of distance 1 from the origin in four-dimensional space, or also as R3 plus a point at infinity. So if you say that if you go infinitely out in any direction, you'll get to the same point, that sort of pulls R3 into a spherical shape. And as mentioned in the introduction, knots in three manifolds, even including three manifolds other than the three-sphere, are things that I care a lot about. But let's get to another example. This is a disk called a disk bundle over a sphere. Over a sphere. So, and this is the usual sphere S2. Basically, we have in black a sphere, and at every point we have thickened it up by a disk. So because there's 2 dimensions for the sphere and 2 dimensions for the disk that's been thickened up by, we get that this is a 4-manifold. And this is a special compared to our other ones because this is a manifold with boundary, which will be a 3-manifold. So the edges of these disks come together to form a 3-manifold themselves. One thing you'll note from this picture that'll come up and be useful later is that, well, this is thickened by the disk. It can be thickened in a twisty way, which I've represented by these disks here twisting around. So those are some examples of things one might study in low-dimensional topology. Oh, and also there is in here a submanifold of dimension 2. That sphere sitting inside our thickened or disk bundle. So one way we might try to study these things is using something called singular homology. And this is an algebraic structure that keeps track of structurally interesting oriented substructures of our manifold. And there are substructures that we get different dimensions here based on the subscript D. So for example, if you look at the zeroth homology, those should be structurally interesting oriented substructures of dimension 0. So we'll look at points, and they're oriented, so they will come with a sign, plus or minus. to pick out what we mean by structurally interesting, we will say that 2 points cancel if they are, if there's a path connecting them, so that there's a negative on one end and a positive on the other. This has the effect that when, as an algebraic object, we'll just get a copy of Z for each connected component of our manifold, because these paths will collapse everything in the same component down to count in the same thing. Now, for the first homology, that's going to be structurally interesting substructures of dimension 1, which will be loops, and they're oriented loops. So here we have 2 examples, and because they're oriented, if we go like the other orientation, that's like taking the negative. And I've chosen these 2 because these really form, for the torus at least, a basis for the first homology, in that if you had some loop that you were looking at, you'd really want to know how many times you went around this way, and then how many times you went around this way. And that actually tells you the structurally interesting features of that loop. And this, as before, we had a way to say 2 things cancel in order to give our definition of structurally interesting. And in this case, 2 things cancel if 2 loops cancel if there is a surface, oriented surface, that has those loops as the boundary, such as in here we have the green loop and the blue loop, and the lighter blue shaded region gives the thing that is really telling us that these should cancel. And at least in our case, they're also canceling because they're going different ways around the torus. Finally, for the second homology, we could look at surfaces in our space. These don't necessarily be manifolds, they could be what's called immersed, but at least we have our surface here that's a structurally interesting substructure of dimension 2, and we will be getting a copy of Z for that. In the case of 4 manifolds, and 4 manifolds that have these nice adjectives of oriented and compact, compact particularly means that there is a certain finiteness condition prevents things from escaping off to infinity. Then, and 4 manifold, then 2 oriented subsurfaces of that 4 manifold will generically intersect in points, meaning not every pair of subsurfaces will intersect points, but if you wiggle them, then you can get them to intersect in points. And these points can be given a sign, because everything inside is oriented, the 2 subsurfaces and our larger space. And we can ask if the 2 orientations on the subsurfaces are compatible with the larger orientation or not. So that would either be a plus or a minus, depending on whether they're compatible. And the sign count depends only on the homology classes of the subsurfaces, and then creates a symmetric bilinear form on the second homology to the integers by doing these counts of intersection points. And this is called the intersection form, which is already allowing us to give extra structure to our second homology that is telling us interesting things about our manifold, how these surfaces inside them interact. As an example, we had a 4 manifold earlier, the thickened sphere. And in this case, our second homology is a copy of Z generated by the sphere. We just count, we can say like take 5 copies of that sphere. Or something, or take 1 copy. And we might want to know then, what is the intersection form of this? And turns out, being how you can push the sphere off of itself in order to have it intersect itself in points is determined by how we do the thickening. And in this case, the twistiness here, it's twisting twice around, in fact, twice in a negative direction. So the self-intersection is here is -2. And in general, that the main thing I want you to take away from here is that the self-intersection is measuring how twisted the disk bundle is. So now I'm going to get to a new idea, which is lattice homology. And this is something we will want to define for a certain class of three manifolds in order to give us information about them, perhaps tell them apart. You can do other things. It'll function like singular homology in order as an algebraic structure that is you can study. And for lattice homology, the motto will be that we are measuring the failure of the integer lattice to approximate a family of ellipsoids. And if you take one thing away, that'd be thing you keep in mind. You might notice here we have our square pegs and our round holes. So this flowchart, we'll be unpacking this idea more through the presentation, but this flowchart already arranges how these ideas will come together. Our family of ellipsoids, they vary by scale and they come from a negative definite intersection form. So here you might be thinking we have a four manifold in the background that has our three manifold as boundary. That's the easiest way to relate have a four manifold and three manifold be related. And inside this four manifold, we'll have a preferred basis of spheres for the second homology. And these will give us our choice of integer lattice by acting on these things called spin C structures. I will go back to say a little bit more on this later, though, or at least how they fit into the picture. Together, these ideas come to give a filtration on Euclidean space. A filtration means that there's a sequence of nested subspaces that fills out Euclidean space. So if you get bigger, you'll eventually get to any point. And then we will take the singular homology at each layer and record the information about how these layers interacted from one including into the next. So as before earlier, I mentioned that we'll have a four manifold in the background. Let's build some up. We already had our disk bundle over the sphere. Let's make something slightly more complicated by gluing two of them together through an operation called plumbing. Take a point in each, to do this, take a point in each sphere, take a neighborhood of that trivializes the disk bundle. So we have two disks. One is from the base, i.e. the S2 part, and the other is from the fiber, i.e. the thickening. And we'll glue those together so that the base of one becomes the fiber of the other. This is a dimensionally reduced picture. I'm drawing these lines to emphasize these lines, when you look this way, look like the base. They're parallel copies of this middle piece. But when you look this way, they look like the fiber. They look like this thickening portion, which is what I mean by that gluing. I'll also note that these two central pieces are now forced to intersect in this point. And in fact, this intersection will be positive. However, we don't just want to plumb two disk bundles or spheres together. We might want to do this a lot of times. So, and we'll record this information using a graph with integer weighted vertices. So here's one. This will represent a disk bundle with self-intersection number -2, as earlier. And then these edges will represent doing this plumbing operation. So these two have been plumbed together, but these two have not. And here, the spheres provide a basis for our second homology. They each are structurally interesting, capturing a key feature of this plumbing. And they really capture the key features. And also the intersection form can be read off of the graph in that on the diagonal, that's self-intersection. So that's what the integer weights that we put on there. And off diagonal, we'll have ones if there's an edge between them, and 0 because we force them to intersect, and 0 otherwise because they would have no reason to intersect. And one thing I'll say is that these general constructions are called plumbings, And they are really great because not only can you get the intersection form easily, but you sort of have the minimal amount of four-manifold material needed to realize this intersection form. So the geometry is going to be very closely related to the intersection form. So let's go back to Latismology. We've been talking about these four manifolds. What I said, there's a certain class of three manifolds this works for. Which three manifolds are those? They're going to be the boundaries of negative definite plumbings. Negative definite meaning that intersection form has to be negative definite. Pairing something with itself that's not zero will always give you a negative number. And these plumbings can be thought of in terms of something else, which are resolutions of normal complex surface singularities, which is this picture down below. Here's the singularity with and normal is a certain statement that this won't be too singular. Complex surface is a type of four manifold. And this is plucking out our three manifold. And we can actually, when we look at our plumbing, we've replaced this singular point with a bunch of spheres in order to get our nice plumbing over here. For this talk, some of my statements will require that we assume that our graph has no cycles. Latismology can be defined more generally than that, but it'll make things simpler on all of our parts. A key class of examples to keep in mind are B-squared spheres. These are defined using three coprime integers, p, q, and r, that define us our algebraic surface with a singularity at 0. And to get our three manifold, we're taking the link of that, which gives us the boundary of a cone-like neighborhood around that point. These are, one interesting thing about these is these are what are called integer homology spheres. They cannot, through singular homology, be distinguished from the three sphere. I mentioned spin-C structures earlier. I'm actually not going to tell you precisely what they are. They behave a lot like second homology classes, but aren't quite. If you know something about cohomology, they behave even more like second cohomology classes, but still not quite. The details of the difference are technical, and you're going to be most of the way there if you think about them in these terms. If you let X be a four manifold, such particularly one of our negative definite plumbings, and look at it have its boundary, then the second homology classes of X act on spin C of X, and the orbits will represent spin C of Y. With our preferred basis of spheres, each of these orbits will look like an affine integer lattice z to the s, where s is the dimension of our second homology. So in this picture here, these dots could be our spin C structures, and green could be action by one sphere, moving us up like this, and blue action by a different sphere, and it arranges this nicely like the integers in Euclidean space. So lattice homology was created by Andras Nemethy. In addition to the vertices and edges of the lattice we had on the previous slide, we can also add on the squares. And if we had a third dimension, there would be cubes that we could add in. And this will give us a cube decomposition of Euclidean space. There is then a height function on the spin C structures that is computed using the square in the intersection form. That is how we get these ellipses. And we'll say a hypercube has the same height as its lowest vertex. This provides a filtration on the space by looking at the cubes that fit inside a given ellipse. You can think of this as super level sets of the height function. We then, we'll take the singular homology of each layer and keep track of how the different layers relate to each other. So let's pull up a bigger slide to go look at an example. So at the 0th layer, we'll have these vertices, and there's actually one more vertex up top there. And we'll also have these edges. And here we have a single connected component. There's not any loops. There's not any interesting surfaces. In fact, this can be squished down to a point, which means that the only homology we'll get is a z for that single connected component. And we can also represent this as a dot. At layer -2, we'll pick out everything we had before. That's what it means by having a filtration. But we'll also be picking out this square because the minimum of this square is -2. This square, there's also another one up there. So note that this also can be collapsed down to a point. Or just in general, it doesn't have any interesting loops in it. It doesn't have, like, there's some box squares, but there's not a closed surface sitting there. So we're going to be getting just another copy of z for that connected component, another dot. I said we're keeping track of how these relate. So let's draw a line showing that this connected component got included into this connected component. On the algebraic side, we would keep track of this with a variable u. And turns out this process continues because there's no where each time we only have that single connected component in this case, because this is coming from an actual example, and you don't get interesting things happening in actual examples until you have at least 4 vertices, which would not be easy to draw. But this is still an example that we could calculate. The thing I'm drawing here is called a graded root. And I said, here's this algebraic structure. I will say that even though you can't get an actual example with it, something interesting, you can, in 2 dimensions, draw something that helps you see what might happen with more wiggle room. Which is, what if this ellipse was moved off of itself a little, so that we picked up those 2 vertices, but now missed that. That's now dropped down to -2. Now, at grading 0, we get those 2 vertices and nothing else. So we get 2 connected components, which is something slightly different. Now at grading -2, we really haven't changed anything that we had, that bigger ellipse. So we pick out everything we had before. And those 2 connected components we had before, they merge together into the larger connected component as such. And then I said, we haven't changed everything farther down. And well, what we didn't calculate this from an actual example. This is the graded root from an actual 3-manifold, which is sigma 237. So we are seeing a case where the integer lattice might not well approximate these ellipsoids. You can get even more complexity, take 2 copies of sigma 237 and stick them together. If on this 0th level of filtration, we'll end up with 4 different connected components in homology 0. At -2, those will become 1 connected component, which I've sort of illustrated here using a single square, which is a single component, but that connected component will actually have an interesting 1 cycle, which I find really interesting because we're approximating these ellipsoids that don't have any interesting 1 cycles, but we're able to get them here by having an integer lattice that's askew. Then at the level of filtration -4, we get back down to 1 connected component with no 1 cycles, and that continues on. So the moral of the story for these square pegs and round holes is that surprising complexity can arise when 2 seemingly simple things interact. For example, these seemingly simple things being the integer lattice and these ellipsoids coming from a negative definite quadratic form. Sometimes 2 structures can appear to be tailor-made for each other, but even a slight shift can disrupt this, like the shift of that ellipse slightly off. And well, this isn't the reason I study these things. There's a nice little metaphor here in that, well, the experience of gender can itself be complex. It gets so much more complex when you have to interact with institutions and systems that weren't built with your needs in mind. And